Yes.
Okay. So this talk is about global regularity estimate for nonlinear elliptic problems with a non-standard growth. So in my first talk, actually I focused on linear problems and nonlinear problems with a standard growth. Now I am moving to non-standard growth nonlinear problem. So let me start with this very familiar P Laplacian problems. So this is energy functional with a P growth. And the Lagrangian equation is, this is P Laplacian problems. So P is the number, and in particular, when P equals 1, this is also very important problems which is related to P equals 1. This is minimal surface problems in the mean curvature flow. Also, P equals 2, this is a harmonic function, right? This is linear problems. And the P equals n, this is related to quasi-conformal mapping, also important case. In particular, P equals infinite. This is infinite Laplacian problems. This problem is now getting popular because it is related to some game theory and the control problems. So anyway, the best regularity for this P Laplacian problem was proved by like Rozhenskaya and Uralsteva in 1961. That is the C1 alpha regularity. So given P between 1 and infinite, there exists alpha depend on P, 0 and 1, such that U has a C1 alpha regularity. Okay, so everybody knows about this regularity. And now, the natural generalization of this P Laplacian problem is introduced by Gary Lieberman in 1991, actually 30 years later. Like, this is so-called to be like G Laplacian problems. Okay, so if the typical example is given by G over T equals T to P and logarithm and gamma power. So gamma equals 0, then this leads to be like P Laplacian problems. Okay. So comparing to P Laplacian problem, this energy density is replaced by this small function G, dW and dW. This is close to the energy density, capital G. G is called to be like a Young function or n function. And this G Laplacian equation is elliptic, except possibly at gradient U equals 0. This is, and if and only if small g is increasing and uniformly elliptic, if and only if this is the condition. There are positive constants, small delta, and g sub 0, such that this condition. Okay. It turns out to be this is a correct condition so that this G Laplacian problem is uniformly elliptic. And this condition is connected to that this Young function satisfies the delta 2 and the Nabla-2 condition. It means that the growth does not grow so fast, nor decay so fast. Okay, and Lieberman proved that given G satisfying this condition, there exists alpha between 0 and 1 such that the solution enjoys C1 alpha regularity. So once we have this condition, we can say almost every kind of regularity result for P Laplacian can be recovered for these G Laplacian problems. So this is a very nice extension of the P Laplacian problems. Okay, so let me go to another extension of the P Laplacian. Actually, from starting this G Laplacian, this is a non-standard growth. Okay, this is the most basic one with a non-standard growth. Another is a slightly more general than G Laplacian problem is PX Laplacian problems. So if you look at this energy density, okay, we have here a variable exponent. P Laplacian, this is constant. Instead, we have a variable exponent. And its Euler Lagrangian equation is the famous PX Laplacian problems. Then, of course, we need some correct condition so that this problem has the regularity. So also it turns out that, okay, the correct condition is that the first one is this Px is bounded below and above. More than the most important condition is it is a so-called log-Holder continuous. And the typical example is given by P of x equals 1 over log 1 over absolute of x. This is the example, symbolic examples. And so this is the correct condition for the PX Laplacian problems. So this is log-Holder continuous. Okay, this is the condition. Probably most of them know this problem, these conditions very well. Okay, so if with a modulus continuity function omega over this P of x, okay, this condition can be replaced by these conditions. This means that this is bounded. Okay, so if we compare like Holder continuity and the log-Holder continuity around x equals the origin, the graph of this function is more wider. It means that this is a weak condition, that Holder condition. Okay, also, so there are so many regularity results in this direction under this log-Holder continuity. There are many regularity results. Then how we can understand, how we can approach this PX Laplace. Okay, so for me, I just localize. I'm looking at very small ball with the center x0 and the radius r. Then this is energy density, dw over x to p over x. This is purely identity, right? +1, -1. Then I have this function px minus px0 times like s. Then applying like a mean value property for this function. Then this is a very basic direct calculation. This one, P over x, can be estimated. This is a constant, plus this is some, like is this error term here. Okay, then let me take the energy here, integration. Then Px Laplacian is less than, this is a constant, right? This is a P Laplacian. Plus, this is a kind of the error term. Okay, but we know that this is the condition for the log-Holder continuity. This is bounded. Then my Px Laplacian is under control by this is P Laplacian and P Laplacian, right? So once this term is uniformly bounded, this Px Laplacian can be returning to the P Laplacian. Okay, so if this is bounded, then we can prove like a C alpha regularity, right? Or Hanning regularity. So with the assumption, this log-Holder continuity, we can prove like C alpha regularity. Of course, we can prove higher integrability for the gradient. Right? This is actually very standard approach. We know very well how we can do this one. Okay, this is already very well observed a long time ago. So, and with a little bit strong assumption, like this is a vanishing condition, we can prove the C alpha regularity for every alpha, of course, less than 1. And to have like a C1 alpha regularity, we need a little bit stronger, like the Holder continuity of the Px, or its modulus continuous function. And another one is also interesting problem is this ellipsis regularity and the continuity criterion. So I know there are many important improvements in this direction, and I just skip. Okay. Then what I am interested in is about LP regularity of the gradient. So for the homogeneous problems, like by using some kind of a perturbation argument, we can prove that for every gamma, any number between 1 to infinite, there exists a small number delta. If this error term is sufficiently small, then we can prove that higher integrability for every gamma. Okay, so then what is the Calderon-Zygmunt theory? Is that if we add the right-hand side is the same structure. Like this is we considering general Px Laplacian problems. This nonlinearity has like a Px Laplacian type growth. Then the natural question is the same as for the linear case. What would be optimal or minimal regularity assumptions on this nonlinearity, in particular this x variable, and the exponent p of x, and the boundary omega, under which we have this kind of Calderon-Zygmunt estimate. Okay, so, and the idea is the simple, right? Because we are always looking at the perturbation argument. Like for the linear problems, if we are preaching, so assuming that we have like a small BM condition, we can preaching x here. And also, if we are looking at the boundary, like we can plot the sufficiently flat in some sense, like in the Liepelmer flat domain, then the arguments from the linear problem can be applied to these problems. So anyway, the most important observation is, let me say this one. So if we are using localization, then we have this one. And once this is sufficiently small, my Px Laplacian can be reduced to P Laplacian. But we know how to handle P Laplacian problems. So this is the way. Also how to prove Calderon-Zygmunt theory. Okay. So in this way, there are so many regulated results in these directions. In particular, with like my former PhD student Jiwon Ok and Sang-Jin Yu, we can prove like the Calderon-Zygmunt theory for this px Laplacian, in particular the global estimate. Okay. So let me go over to so-called the double page problems. So in the previous slide, so we just look at the px Laplacian. So again, in very small ball, we can roughly compute this px energy density. So like by using this is a kind of a Taylor expansion. Right? So this is a px, and this is a variable. Px, this is a variable, this is constant. And this term, we have a logarithmic growth. Okay, so we know that the condition for the px Laplacian, this is log-Holder continuous. So for this particular, for this kind of energy, the correct condition for this one is like so-called to be like modulating function. This is log-Holder continuous. Okay, and with this observation, we can naturally considering this so-called double page problems for the borderline case. So here, the first part is this is a P Laplacian, like polynomial growth. And the second one, this is like a P growth times logarithmic growth. So this, the integrand switch between a type of a polynomial and a type of a logarithmic according to the modulated function a of x. Of course, we know that the condition for the ax is a log-Holder continuous. But if we look at this energy, the size of a gradient is sufficiently large, right? There is not much difference, this polynomial and the logarithmic growth. So for this way, so this is called to be a borderline case, very mild transition of the energy. So again, here, right, my px Laplacian is very close to this double page for the borderline case. So once we observe this approximation, we can almost assure that almost every kind of px Laplacian problem, the regularity for this one, right, can be extended to this borderline case. Okay, so in this way, of course, there are many regularity results, including with my former student, Jian O, we can prove a global Calderon-Zygmunt estimate. Okay, the same condition as for the px Laplacian problem. And then this is, nowadays is so popular. It is truly like double page problems with a P and Q page growth. Actually, this problem has a long history, but when it comes to like a labyrinthine phenomena and some existence, uniqueness, blah, blah. But I am just focusing on the regularity. So let me start with a very remarkable development was given by Colombo and Minzona, like 5 years ago. They started investigate this particular, this is double page problems, PQ here. Okay, then its Euler Lagrangian equation can be here reduced to this one. Then the natural question, the first important thing is that what is necessary and the specific conditions for this energy functional so that we don't have a labyrinthine phenomena. And then, so they figure out, they found this condition. Of course, Q is bigger than P. And the A over X is a C alpha regularity. But we know that, right? Q is not far away from P. So this is the correct conditions. if we considering like a bounded solution, then this can be extended a little bit. Okay. So what is the main observation by them, Minjona and Colombo, is I would roughly say that. So just localize. And there are two alternatives. First one is, of course, this modulate function is very important, right? The most important one. So we classify two cases. The first one is almost one, away from zero. Then this energy is very close to dWp, dWq. Right? And this is for what? G-Laplacian problems. And the Young function is given by T2p plus T2q. Right? This is G-Laplacian problems, purely G-Laplacian problems. Then we know how to handle these problems very well. And the more difficult case is A of x is like x to alpha. Okay, then first we have to check that, like the higher integrability, like that the solution for the homogeneous problems its gradient belongs to LQ. Right? So the second energy here, AX and the absolute value dWq power. This is direct computations because AX is to alpha here and the energy. Okay. And if we do have this inequality, then we do have a PPQ, right? This is a higher integrability. And once we do have this inequality, then this is a direct computation. Okay, it means that the second energy is under control by this first energy, P. Okay, if and only if this part, okay, 1 plus alpha over n minus P is bigger than 0 or equal to 0. Okay, because this term is getting smaller as R is getting smaller. Okay, so assuming that we have this kind of inverse Holder inequality, then the problems returning to the typical P Laplacian problems, and then we can do blah blah. Okay. So this is, I think that this is the most important observation for this double page, in particular PQ growth. Then we are going into our investigations for the regularity. So by this observation, like Minjona, Colombo, they proved the C1 alpha, and later, actually including the borderline case here with the Baroni, Minjona, Colombo, like the 17th. Also, in particular, I am very interested in this is Calderon-Zygmunt theory, and this is interior case. Then with my former student, Chen O, we have extended this interior regularity is a global Calderon-Zygmunt theory, but here we have assumes like a C alpha coefficient because here this is including like a modulating function. So in this case, it must be C alpha. Also here we have used like a flattening argument because we just follow the approach by Minjona and Colombo in this case. So that's why the domain is very nice, like a C1 beta domain. And then now we are thinking, so the question is, can we relax the coefficient like discontinuous? Or can we use non-smooth domains like a Reichenberg flat domain? So our question started from kind of problems. And then we just separate the nonlinearity. Why not? Right? So like if A of x is completely 0, then this is the P Laplacian problems. So we separate. This is the first energy and the second energy, But the first energy is like P Laplacian, and the second energy is Q Laplacians. So once this PDE is separate, then the coefficient, of course, can be allowed to be just discontinuous, possibly just measurable in one direction. Okay, so in this way, we have we are able to prove like the global Calderon-Zygmunt theory under the assumption that here we have used the small VM assumptions, this variable and this variable. And the domain is like the same, like delta Reichenberg flatness. And this is with my student, Mingyu Lim. So let me sketch how to prove this one for the global Calderon-Zygmunt theory. Well, of course, we are using perturbation argument. Then there are three parts we can do freezing. So here, first one, this is x variable, first. And the second one here, second energy, x here. And the third here, marginality functions. So we have to very carefully select the order, how to freezing. Like here, x, x, x here. So let me just sketch the proof. The proof is, the idea is really simple, but the computation is really, really complicated. Just I give the idea. So first, just start homogeneous problems, like the right-hand side equals 0, okay? Then the corresponding solution has a higher integrability. Of course, if f is small, then the difference from solution is also sufficiently small. And then next the freezing here, because we have a small VM assumption, like x here and x here. And the freezing. And then later, I'm looking at the conditions for the domains. It is sufficiently flat here. And my definition is that the boundary, the locally boundary part is very close to here, the hyperplane xn equals 0. Okay. Then by using like the weak compactness, we can go back to this wiggly part, the boundary can go to the, here, this part is a very flat boundary. Then of course we can prove the comparison estimate. So once we reach here, then finally we're freezing A over X. Then the limiting PDE has, we know that Lipschitz regularity from the previous result from Minzona and Colombo. Then everything is working. So in this way, we are able to prove a global Calderon-Zygmunt theory. Okay. And then the next question is why not, right? This is a P Laplacian, Q Laplacian. Then we are extending Px Laplacian and the Qx Laplacian. So of course, the Euler Lagrangian problem is here, Px Laplacian plus Ax Qx Laplacian. And then of course, this is, we can approximately compute the local energy. Okay, dWpx plus Ax dWqx, like the computing, like the Px Laplacian, the same. So Px0 and the Qx0, and this is the error term. Okay, this is term, log Holder continuity term. Another, this is a log Holder continuity term. So if R is sufficiently small, okay, then from the assumption, this error term is sufficiently small. As R is getting smaller, this is like a Px, Qx double page problems is going to like a PQ double page problems. Okay. Then almost every kind of regularity result for the PQ double page can be recovered to here. This PX, QX double page problems. Okay. Of course, this local computation is very important. Then we can going on, right? First, finding the correct conditions for these double page problems. Now this is the condition is quite easy once we reached here. A of x is wholly continuous, and the px over qx is bounded below and above. Of course, qx is stronger than p over x. And the modulus continued, and the row holder continued. And this condition, of course, this condition is uniformly for every x here. Okay, so PQ double page problems can be translated to this PX, QX Lagrangian. So we further assume that this is the smallest assumption and the basing assumption and the row holder continuity, right? Depending on the desired regularity result. Okay, then we can recover almost every regularity result for the PQ double page problems in this PX, QX Laplacian problem. Okay, and this is someone is already proved, and some regular result is underway with my student Hoshik Lee. And then let me tell you the last examples for the double page is so-called G and H page. So with the two Young functions, capital G and capital H, we are considering this double page problems with the G and H growth. And the typical example is G to T equals T to P and H over T equals T to Q. Then this is the PQ double page problems. So this is a natural extension of the double page of PQ growth. And then the most difficult part is that what is the correct condition for this double page problem under which we don't have a labyrinth phenomena, or we can recover every kind of regularity result. Okay, anyway, the basic assumption for these two Young function is the same here, right? Capital G is delta 2 nabla 2, and the H is stronger than G, equivalent to this condition. Then you are trying to find the correct, possibly necessary, and sufficient condition for these double page problems, and we are able to prove that under this assumption, okay, under this assumption, many kind of regularity results in the PQ double page can be recovered to this GH page problems. Okay, this is very reasonable. Okay, so particular for this specific case, this conditions is exactly the same as a PQ double page problem. Okay. Then under this assumption, like U is bounded, then this condition is corresponding. And another condition, like a strong assumptions, like a holder continuity, then the condition can be relaxed like this one. Okay. Then the next our project, the next natural question is that under like these conditions, this one, this one, this one, can you prove C1 alpha regularity for these problems? And my answer, yes, it is. So of course, it is very complicated. But anyway, so our observation actually comes from the observations from the Palombo and the Minzona. Actually, they are PQ double page problems. Okay, again, we have two alternatives. Okay, so you first localize this energy. Then the argument depends on whether A of x is 1 or x to alpha. And for the easier case, AX is close to 1, then the second energy is close to like this H over dW. And then these problems can be reduced to H Laplace problems. This is just H Laplace problem. We know, once we reach the know, we know how to handle this H Laplace problems. And the difficult part is here, the second alternative, A of x is close to x to alpha. Then we need a higher integrability. So let's just do the computations. So this is the second energy, AX and HDW. Okay, and A of x is close to here, R to alpha. And then multiply R to n divided by R, take the average here. And then the next step, if you are able to estimate this one, H energy under G energy, okay, then this is just a direct computations. So if you look at this power, alpha over n minus theta, this is a positive, right? This condition. Then this can be reduced to G Laplace problems. Okay, so the most important observation from here. Then let me go back to our assumption here. Okay, this assumption. Okay, because of this assumption, I would say this is true. Okay. So this very simple observation can imply a lot of many regularity results. In particular, so we are able to prove like C alpha regularity and the Harnack inequality, even more C1 alpha regularity for the three cases. Also, we can prove like the Calderon-Zygmunt theory. And this is doing very recently with my student, Basan Dorotz, and even my former student, Jian O. So maybe it's, I still have 10 minutes. But okay, this is the end of